this video we are going to look at another example of a question that uses the SUVAT equations. So we've looked at the SUVAT equations in the previous two videos. We did an example question in the last one. We're going to do another one in this video, but it's going to be a little more complicated, but still not too bad. So let's look at the example. A fly is flying in a straight line at a speed of 13 meters per second towards a fan that is 60 meters away. The fan is blowing air at the fly, causing it to decelerate at 2 meters per second per second. For how long is the fly 20 meters or closer to the fan? So it's a bit of a wordy question. Let's try and draw a diagram of what's going on to get a better picture. My advice would always be to draw a diagram in questions like this because it just lets you know what's going on. So it doesn't have to be a neat diagram. Let's just draw a quick diagram. So this line is going to represent the path that the fly is on, because the fly is flying in a straight line, so we can think of it as just a straight horizontal line. We'll mark the origin, which is where the fly starts. So the fly will start at O, the origin, and we'll mark the position of the fan. So that's at point F. That's where the fan is. And so we're going to say that this is the positive direction. The fly has 13 meters per second initial velocity. That's a positive number, so it makes sense because the fly is flying in this direction to call this the positive direction, which is pretty standard to just say the positive direction is the direction the thing is moving in. So that's 60 meters. Let's also mark 40 meters here. I mean, this is just me roughly marking it. This might not be exactly 2/3 along the line as it should be, but roughly it's 40 meters. The diagram doesn't have to be completely accurate. So I'm marking 40 meters because we care about when the fly is 20 meters or closer to the fan, which is exactly when it's moved 40 meters or more, because it starts 60 meters away. So it's when it enters this region. So how long is the fly in this region? That is essentially our question. So let's try and figure it out. The next thing to do once you've drawn your diagram is to write down what you know and what you don't know. So write down which of the variables in the SUVAT equations you already have. So do we have displacement S? Well, we do, because since we want to know how long it's in the region marked with the red lines, it's best to initially find out how long it takes to get to 40 meters. So how long it takes to move 40 meters, because then it's within 20 meters and it's got to the start of this region. Then we can figure out how long it stays in the region. So we'll say that displacement, at least what we're concerned about first, is 40 meters. U, the initial velocity, is given. It's 13 meters per second to the -1. So both of these are positive because they're both in the positive direction away from the origin. The final velocity, well, when it gets to 40 meters, we don't know what that is. We've not been told. So it's unknown. The acceleration, we're told, is 2 meters per second, but it's decelerating, so it's slowing down. So that has to be in the negative direction. So it's -2. So you can think, if you like, as the acceleration acting against the fly because it's trying to slow it down. So if you have a positive velocity but the thing is slowing down, it must have a negative acceleration. So we have to call it -2. And then the time is exactly what we want. So we don't have it. So we need an equation now that will give us time that uses S, U, and A because they're the things we already know. So that is this equation here. I'm not writing down all the SUVAT equations or bringing them up on the screen because there's quite a few of them, but you should have them in front of you hopefully as reference. If you have a list of them, you should hopefully see this one on there. It's got U, A, and S in it, which is what we have, and then T is what we're trying to find. It's also got T, and it doesn't have V, which is important. So let's just plug into this equation what we already have. So S is 40, that equals U times T, so that's 13T. So I'm just reading these off my list. And then that's plus 1/2 times A, but if A is -2, then 1/2 times A is -1, and then that's times by T squared, so I just get -T squared. If I put everything on one side, I get this. I can see it's a quadratic equation, T squared minus 13T plus 40 equals 0. If you don't know how to solve a quadratic equation, you should go watch the algebra set of videos in this series because in there we talk about solving quadratic equations. I'm going to assume that you can do it for the purposes of this video. So we factorize and we get T minus 5 and T minus 8. This gives us our solutions for T. We get 2 of them. T is either 5 seconds or it's 8 seconds. Now if you think about the problem, getting 2 times makes complete sense. So you always get 2 times when you have you often will when you have a quadratic, because you can get two solutions. But it makes sense because the fly has a constant deceleration, which means it's constantly slowing down until eventually it stops. Under our conditions that would happen, and because we're considering the deceleration to be constant, the deceleration would continue, which means it would actually start to move in the opposite direction. So at this point it's actually getting quicker, but it's still going to have a minus acceleration because it's moving in the negative direction now. So that means that it's going to pass the 40 meter mark at one point, and then eventually when it stops and starts moving backwards, it'll pass it again on the way back. So we hope that that's what these two times are. And if so, then probably we've found our answer, because if it passes into this red region at 5 seconds and then exits again at 8 seconds, in total that's 3 seconds it spent within the red region. 8 minus 5 is 3. But let's check this with some extra information. So let's first find the direction of motion at 5 seconds and 8 seconds. So for this we're going to use this SUVAT equation here. So if you look on the right, I've brought up a second one. V equals u plus at. I've got u, a and t. I've got two different t's. I'll check both of them and I'll find v in each case. So it's velocity at the times. So when t is 5, I get v equals 13 minus 2 times 5. So this is just plugging in everything I have into the SUVAT equation, and that's 3. Now I don't care so much about the 3, what I care about the fact it's positive. If it's a positive velocity, then that means at 5 seconds, when it initially reaches the 40 meter mark, it has motion in this direction, the positive direction. So it's going towards the fan still. But at t equals 8, I plug in and I get v is 13 minus 2 times 8 now, and that's minus 3. So the motion is now, because it's a negative velocity, it must be moving the other way away from the fan. So 3 seconds later, after crossing the 40 meter mark, it's crossed it again in the opposite direction. So that looks good. Let's now check the time the fly changes direction. So how long does it take for the time to change direction? Well, for this, we are going to plug v equals 0 into the second SUVAT equation, because at the time the fly changes direction is when it stops for an instant before moving back the other way. So it slows down, slows down, slows down until eventually it stops and then starts moving the other way. So it's when its velocity is 0. So plug that in, we get 0 equals 13 minus 2 times whatever the time is. Rearrange and we get the time is 6.5 seconds. So that's just a simple rearrangement of that equation to get t. So that makes sense. It crossed at 5 seconds. A second and a half later it stopped. A second and a half later it went back over the 40 meter mark, going the other way, away from the fan. So the one final thing we want to check is where was it when it stopped? What was its position? Because we hope it's between 40 and 60 meters, because that means this entire time it's been inside that region. If it got all the way through the region out the other side and stopped somewhere after 60 meters, we've got a problem. We don't think that's what's happened, but let's check. So the position of the fly, so we have to use the first equation again because that is for position, and we now have t, it's 6.5, because we want to know the position when the fly changes direction, and we just found that that's at 6.5 seconds. So plug everything in, 13 the initial velocity times 6.5, and then again it's minus because the half and the minus 2 for the acceleration cancel out, so we get minus 6.5 squared. Do this on a piece of paper, in your head, on a calculator, you'll get 42.25 meters. So good, because that is within the red region. So what the fly has done, let's sum up exactly what's happened. After 5 seconds, it's still flying towards the fan, and it crosses over this line where it's within 20 meters of the fan. So start the timer if you like. Then it only moves to 42.25 meters, so still within this region, well within this region, before it stops and starts moving back the other way. And at 8 seconds, so in total 3 seconds after it entered the region, it's exiting the region going back the other way. So in total, exactly as we said, that is 3 seconds. So the answer, if you look at the question, was how long is the fly 20 meters or closer to the fan? 3 seconds. When you get a problem like this, you'll probably get it as, in several parts. So it might be part A is find the time it reaches 40 meters. And then part B is when does it come to a stop? Part C is where does it come to a stop? And then part D is when does it exit the region again? And then therefore you can say in part E, it'll say how long was it in the region for? So it'll probably break it down. I've just done it all in one big go just to show you exactly how a problem like this works.